All right, the next team that we have to present this afternoon is team number 11, the Shipless Skippers.
Good afternoon, everybody. Thank you for coming today. We're the Shipless Skippers. To my right, we have Jenny Plant, Addie Bonus. To my left, we have Trip and Joe from the boat team, and I am Nick. And this is our project, the autonomous sensor boat for our customer, Michael Louie. And Joe is
So the purpose of our project is to design a plug-and-play sensor interface with the ability to take measurements simultaneously from multiple sensors and to interface it with the ECE autonomous sensor boat. It's intended as an educational tool for middle and high school students and to garner interest in science and engineering.
So the need for this, so the ECE autonomous sensor boat has already the ability to operate autonomously, but it does not have the ability to, in addition to its operation, collect data automatically. In addition to that, many high school students, they have very little experience in hands-on applications of science and engineering, or in terms of mathematics, that as well, outside of chemistry and physics classes. And in the United States, we're actually very terrible at teaching our students how to practically apply things like that. And so the focus of these classes are often fundamentals rather than like interesting and practical applications. How many times in these classes have you just sat there and, I don't know, just played with instruments, you're not exactly sure what you're doing? And these experiences can deter students away from these sciences, and having them design, build, test, and then go out to the real world and see what exactly these instruments can do should provide both exciting and educational experience, and hopefully encourage students to pursue engineering sciences and engineering.
This is our overall block diagram of our project, and so just to break it down for you, there's the sensors are connected to the sensor interface, which communicates via SPI to the signal or computer, which is the router processor, the 35. And the camera block right now is not currently implemented, but is inches away from being ready. And we have the existing GPS, which was already implemented on the Rabbit, the Rabbit, and same with the RF transceiver, which communicates with the computer via the COM-port program we developed for this project. And, okay, so at the heart of our project is the sensor interface, which is going to read in from up to 8 sensor slots, and we're going to multiplex that data. You know, we want to pull it. I think our requirement is like each sensor gets read once every 2 seconds. I think we hit once every second. So the sensor interface runs off an MSP 430 processor, which we chose because it has lots and lots of pins, analog to digital conversion, SPI capabilities, everything we needed. The sensor interface itself consists of the processor hooked up to a multiplexer and an array of switches which control which sensors are enabled and how many probes each sensor wants. The one probe that we were given at the onset of our project was a 4-element temperature array, so we needed to be able to pull 4 probes from that, so we pretty much gave that capability to any sensor that's attached. The MSP's responsibility are multiplexing using an off-board analog multiplexer. We just provide the select lines, analog to digital conversion, and then communicating with the Rabbit through SPI results. Here's a picture. You can see lots of switches. So this here would be the enable switches, which tell which sensors are currently plugged in. 1, 2, 3, 4, 1, 2, 3, 4. Same on the other side. These are represent the amount of probes each sensor has. With both of the switches here correspond here, and they're both high in 4 probes. They're both low in 1 probe. It's a binary representation. I have one amount of probes that you're trying to read, and then you will be reading this only. Oh, and there's exactly what I just said, and I'm not trying to get you to understand for it. Yeah, I'll do this already. So we just got to read in the sensor state. So the probe count will be read in, and if if there's only one probe, we only need to do one cycle on that particular sensor. So we record that. We need to control the external sensor multiplexing going to the outboard analog multiplexer as well as internal for the multiple probes on a single sensor. And the other two we are going to church about this now. The way the Rabbit was set up before was it was pretty much the brains behind everything before we came along, and it had the whole menu on it, and it just interfaced with Hyperterm or Teraterm, which is just just reads in COM port values and you can enter a key and it sends it immediately. So we wrote a console application that runs on the computer, and what it does is it takes all of the menu items off of the Rabbit and puts them on the computer, and it also, in making this application, we created a transfer protocol for acknowledgement of getting the command versus if it didn't get the command. So say you press 1, you want to see the GPS coordinates. First, the computer goes through the code and says, okay, you press 1, and it sends command A1, and then the Rabbit sends back 1A as the confirmation, and then you're all set to go. And so that is the acknowledgement, and then the other thing the COM port program does is it allows you to read the sensor values, and it just reads them through data sentences, and same with all the data that comes in through the program, just data sentences. And it also, we're able to collect data every second off of this console application, just using a loop. Yeah, one of the main parts was to come up with a sensor standard, something so people get to add on to, build their own sensor and apply it to the system. So we need some sort of standardized connection and the voltage levels and everything. So this is the sensor standard we came up with. Maximum of 4 sensor elements or probes. That's because we're only providing 2 internal multiplexing lines. So any more than that, we don't know how to differentiate between them. Output voltage, 0 to 3 volts analog voltage. That corresponds to our MSP 430's analog to digital conversion range. The connector we used, male D-sub connector, you can see we have a bunch of not connected, but we've got ground, MUX1, MUX0, and E out. Pretty simple. You can see it outside during the demo. The PCB sizes can be about 4 by 5 or smaller. That's just so they fit in the boat and the kind of sort of array we have mounted in there. And they must be battery powered. 9 volts worked fine for the temperature array we built, or that was given to us, the pH probe we built, and the division sensor we built. So it's just a suggestion.
Alright, as Nate just mentioned, we built a pH sensor and a turbidity sensor, so I'll talk about the pH. So the overall goal for our sensor development was not only to create these sensors, but also to have them be a template for future students. So to do that, we tried to use common and accepted practices when it comes to circuit design and PCB layout. For this pH sensor, there are 2 main components versus the electrode. Basically, that has 2 chambers that have wires suspended in them. And if you directly measure the potential difference, and according to that equation, it's linearly related to the pH. Now the pH meter, the design was based on instrumentation amplifier, and this solves the problem of the impedance mismatch between the electrode and the meter. We also use the JFET input stage op-amps for our input buffer. And as per our sensor standard, our output voltages are 0 to 3 volts. Through calibration of the electrode and through analyzing the circuit, we were able to come up with that pH voltage characteristic. So users can read out voltages and convert it to the corresponding pH.
of the amount of suspended particles in a body of liquid. Typically, they measure a body of water, which causes cloudiness or haziness, and decreases the ability of light to pass through water. This is an issue because, well, if you're talking in terms of rivers, lakes, or streams, when the higher the level of turbidity, the harder it is for light to penetrate the bottom of the water, which means that plants that grow in these bodies of water cannot actually flourish and develop, meaning that animals such as specific fish and other sorts of life that cannot get the nutrients needed to survive. In addition, high levels of turbidity also cause disease among fish. It also lowers the amount of dissolved oxygen, which is the concentration of oxygen, gaseous oxygen in the water, which I can imagine you can understand why that would be an issue. And so this is a cross section looking down of the turbidity probe. This is the design that I came up with, because in addition to coming up with the circuitry, I also needed to develop the probe, because a turbidity sensor, the sensor itself, costs at least $1,000, which is the entire budget for your scene design project. So what you see here is an nepheliometric turbidity sensor. It's a ratio design, and what makes an nepheliometric turbidity sensor is this photodiode at 90 degrees incidence to the light beam. And what we used, so I made my design based upon the EPA 180.1 and the ISO 7027, both restrict the general turbidity standards. And so what we're using is, it's near IR, so it's actually IR. It's it's 860 nanometers LED, and so the way that this is calculated, as you can see down there, is the voltage level corresponding to turbidity is the 90 degree detector that you see there over the transmitted light. Now, what this does is it scales the turbidity, the voltage corresponding to turbidity, such that so what you do is you take out any skew caused by any reaction due to, sometimes there's a reaction caused by just reaction to colored particles. So that's what the ratio design does. And the IR, this design can calculate turbidities between 0 and 4,000 NTU, which is a proper range when you're looking at rivers, lakes, and streams, because high turbidity is caused by runoff, urban runoff from gutters. It's caused by decay from just the riverbank, and you're talking about like during the spring. Also, it's oftentimes during dry floods, a lot of stuff goes into the river. The typical pH for the Charles River, I can't exactly remember when the study was done, but it was done over about a week and a half time, was over the entire length of the Charles River and the Charles River Basin was 1.9 NTU to 7.3 NTU, and NTU stands for nepheliometric turbidity units. It's the standard that the EPA uses. And so what you see here is that I have two 90 degree photodiodes. What I'm just doing is they go into a summation amplifier, and I just divide them in half. I pretty much average the two, just saying to take care of any difference. And then it just computes it just divides that. And then I scaled it, but I made it so it wouldn't go over 3 volts using a Zener diode, which in actually ended up scaling the output voltage to between 0 and 3 volts.
For that.
Sure.
All right, so we were given the boat with the Rabbit microprocessor, which controls, the GPS, compass, rudder, and RF link. And as previously mentioned, we added on the MSP430 and the sensors and the way the Rabbit, and then the Rabbit also talks to the Comport program. And the thing that links all of this together, the way the Rabbit and the MSP430 talk to each other is with this SPI protocol that we implemented. So the Rabbit runs as the master in 4-pin SPI mode. So there's one line that transmits from the Rabbit to the MSP430 and one that transmits the other way. And there's a chip select line and a clock line. So since the Rabbit is the master, every time it wants to transmit, it sends its clock signal to the MSP430, and the MSP430 it has a transmit buffer and a read buffer, and it sends its transmit buffer to the Rabbit every time, and the Rabbit can choose to read that buffer, or it can choose to write to the MSP430's receive buffer. And so every time the MSP430's receive buffer changes, every time we write from the Rabbit to the MSP430, we go into an interrupt handler, and that looks at its receive buffer, and this byte in the receive buffer, this is going to be our request to retrieve a specific sensor or Nate's enable byte or probe enable, and then depending on what the Rabbit sends, the MSP430 in this interrupt handler, it sends the appropriate data back, and then this data is then stored in the Rabbit in a temporary variable, and that is sent over the RF link back to the PC that's offshore. So basically, at the end of all of this, what we have is all we have to do is in the computer, the console program, as you saw in that menu, we just put a command to request the sensors, and it sends that to the Rabbit, which sends it over SPI, the MSP430, which goes into the interrupt handler and gets the appropriate data, and then sends it from the sensors, and then sends it back, all the way back, so it displays it to the user on the console program.
And before we jump right to questions, I want to give special thanks to both Professor Kia and you, Paul, for helping us sort through the Rabbit.
So on the laptop, do I get voltages or do I get the science? Does it give me NTUs and pH or?
Right now, you're going to see voltages. It's no far leap to just go in there and put the mathematical formula for the sensors we have, the sensors we provided, or whatever sensors you add onto it. It's pretty straightforward. All it is some string formatting, but right now, voltages.
And are your new sensors integrated with the temperature sensors so that they can be operating at the same time?
If you had all the relevant tables, yes.
Now, back to that, you guys made mention of the 0 to 3 volts with the computer interface.
Yep.
Do you have any kind of isolation between the sensor input to the G-sub and the chip that's reading these numbers? Because if you're handing this out to high school students to play with, it might be I don't know if you guys consider this, but they have a tendency to wire things backwards.
Yeah.
That would have expanded your options.
Well, I can
you guys like tested this somehow?
What do you mean, like, in the
Is it,
lab,
like-
yes?
No, no, like in water?
Oh, no. Well, I mean, we had to.
It's a boat, shouldn't it be
But
tested
since
in
the
water?
sensor interface has been implemented, I mean, we were kind of, you wanna help us carry it out later, maybe you and me?
I mean, is it now just put in some water?
So you mentioned that you've come inches away from implementing the camera module. Can you maybe just explain how far along you are with the camera, what the camera module does?
Camera module is a stereo RS-232 little camera module that has onboard JPEG compression. So you have the option of 640 by 480, those numbers are right, and 320 by the other one, but 320 by 240, and so it goes down a lot further. But we implemented it on the computer with the just a variation of the Comport program, and we're able to sync with the camera, get the data from the camera, and display a JPEG image using the C++ program. And this is significant because to implement it on the Rabbit, we only needed to know the protocol. Well, we knew the protocols. We just needed to know how to implement the protocols because the documentation for the Rabbit with the camera really was. I mean, at first glance, it seemed great, but it really was not the best documentation. It didn't have any help implementing it into any sort of code or anything. But so now that we have it on a some sort of and we have a program that can do it in C++, we can then port it over to Dynamic C with I don't think it'll be that hard, but something bad can happen.
How many custom PCBs did you design for this project? It looks like there were several.
Two. It was just two. We were gonna do a third, but then it was like the last.
So these were one for the pH sensor and one for the temperature sensor?